Okay guys, welcome back to Organic Chemistry 2. In this chapter, as I promised, we're going to discuss chapter 18. Okay? And a little bit later I'll post these on YouTube so you can play them at your convenience. This chapter is entitled Ethers and Epoxides, which is the main focus. We also have thiols and sulfides, which you'll see towards the end of the chapter. Now let me just give you a quick rundown or summary of what these things are. To begin with, an ether is characterized by having this particular functionality. In other words, a carbon-oxygen-carbon bond. Okay? And the hybridization of these carbons can be either sp3, sp2, or even sp. Epoxides are special kinds of ethers in that they also have a carbon-oxygen-carbon bond. However, the oxygen is part of a three-membered ring. You may remember this back in Organic 1. If not, we'll go over these things again. Typically, the hybridization of these carbons, although it doesn't have to be, is sp3. These species are very, very reactive, as indicative of the angle strain imposed by the three-membered ring. Thiols, as the name sort of suggests, is the sulfur counterpart of an alcohol. You may remember in Organic 1 and also back in chapter 17 that an alcohol is characterized by having an OH bonded to an sp3 carbon. A thiol has an SH bonded to an sp3 carbon. And so the chemistry of thiols in some cases is similar to that of alcohols, but by the same token there's enough differences that they deserve their own discussion. Sulfides, like ethers, okay, are characterized by having a carbon-sulfur-carbon bond. And again, so long as you have this functionality, you would be considered a sulfide. So it's the sulfur counterpart of an ether. So we'll look at those things, and mostly these things towards the end. But for now, what I'd like to do is segue into some of the names and properties of ethers. So let's move down the page. I'm looking at section 18.1. where it says names and properties of ethers. Let's first spend a little bit of time discussing the properties of ethers. I have a couple bullet points there, right? And let's read those. The first bullet point says ethers tend to have higher boiling points than their hydrocarbon counterparts. And there's a simple reason for that. It's because they're more polar. Okay. Now, let's just keep in mind what's going on here. You remember what a boiling point was? A boiling point is when you have a liquid vapor equilibrium at some pressure P. Okay, that's a boiling point. And again, it's because they have a greater level of polarity than do hydrocarbons. So if I ask you in an exam, which I may do, why do they have higher boiling points? And the answer is pretty simple. Because they're more polar. So let's just look at a couple examples of this, okay, so that we can wrap our brain around it. Now, if you look at an ether, a generic structure of an ether, let's remind ourselves that the carbon, okay, is bonded to, both carbons in this case are bonded to an sp3 oxygen. And recall too that the optimum bond angle for sp3 is 109.5. However, here that angle is a little bit greater, and because of that we have an incipient polarity. So we could draw a dipole that runs right through there, okay, indicative of that polarity. So let's take a look at just a few examples. And folks, don't memorize any of these temperatures. I just want you to see what's going on. In the left-hand column, I have an ethers, 3 of them, and I have their respective boiling points. In the right-hand column, I have a hydrocarbon that we're comparing these to, as well as their respective boiling points. So let's just look at an example so that you understand what I mean by a hydrocarbon counterpart. This is dimethyl ether, and notice what we have in the center. We have an oxygen. This is propane, and what do we have in the center here? A methylene. So henceforth, these are counterparts of one another. What's the boiling point of dimethyl ether? -25. Okay? So this is actually a gas at room temperature. What's the boiling point of propane? -45. Okay, so you can see that the ether has a higher boiling point than does the hydrocarbon. So this is just one example of that. Let's look at the next example. This compound here in row 2 is something you may remember seeing, we saw back earlier. This is tetrahydrofuran. This was the solvent actually that we were using for the Grignard reaction. And we said it was an essential component of the Grignard because it's an ether. Notice here we have an oxygen, but if we move over to cyclopentane, we have a methylene. So these are related as counterparts. And let's look at their boiling points. 65 for THF, 49 for cyclopentane. Hence, the boiling point is higher for THF than it is for cyclopentane. Just one more example. This compound here, notice we have an aromatic ring, an oxygen, and there's our methyl group. This is a simple monosubstituted organic compound known as anisole. Okay, this is a common name. It's called anisole. If we looked at its hydrocarbon counterpart, in other words, replace that oxygen with the methylene, then we simply have ethylbenzene. But once again, you can see the distinction in the boiling point. This boils at 158 degrees Celsius, whereas this is 136. So you might notice again that all these examples in this left-hand column have higher boiling points than all the examples in the right-hand column. And why is that? Because all of these are ethers, and they're much more polar. That's pretty much all I want to say now about the properties of ethers. I'd like to focus the next couple of pages on the nomenclature. And there's going to be 2 types of nomenclature here. One that's very simple and one that requires a little bit more of our imagination. But if you're good at nomenclature, this is going to turn out to be very simple for you. So let's take a look at some of the examples that I have here under the category that I call simple ethers. Okay. Now, if you have a simple ether, in other words, you recognize the R groups that are attached to the central oxygen, all it's necessary is to do here is to alphabetize if you have 2 different organic substituents. Okay. Now, if you have 2 identical organic substituents, you just have to place the word di in front of them. So here's a case in point. You may recognize, I know you do, that on both sides of this sp3 oxygen, we have ethyl groups. There's an ethyl group on the left. There's an ethyl group on the right. So what would you call this? Yep, diethyl ether. Okay. So if these were both methyl groups, you would call it dimethyl ether. If they were both propyl groups, you could call it dipropyl ether, so on and so forth. So this is just one simple example. Okay, and that's why I'm calling it a simple ether. Now, the one in the middle is a constitutional isomer of diethyl ether. It has the same molecular formula. However, it has very different R groups. But these are some of the R groups that you've committed to memory. Let's just look at those. What is this? This is a propyl group, right? Okay. And what is this? This is our good friend, the methyl group. So, the groups are different, So like I said here in the directions, all you have to do is alphabetize the two different organic substituents. So M precedes P in the alphabet. So this is methyl propyl ether. And notice we have three words there: methyl for this one, propyl for that, and then we finish it up with the word ether. So we have three different words here to describe everything. The last one is not that different than the middle one. Now you want to remember that if you see a monosubstituted benzene ring, okay, like that, that's called phenyl, right? That's called phenyl. And here again, we have a methyl. So check the alphabet. M precedes P in the alphabet, so this is methyl phenyl ether. So this would be a systematic nomenclature, okay, for that particular compound. But like I mentioned moments ago, this has a common name, and the common name is anisole. All right. You don't have to commit that to memory. If I ask you to name it, you could call it methyl phenyl ether, or if you do remember it, you can call it anisole. Either name is fine. So let's go ahead now and take a look at the two at the bottom. These are, again, examples of simple ethers because we recognize the R groups right away. Notice here we have a phenyl group on this side, a phenyl group on that side. It's a symmetrical ether. So just like this is diethyl ether, what would this be? This would be diphenyl ether, two words, diphenyl ether. So that's how you name symmetrical ethers. The one in the lower right hand corner of page 101, okay, is not symmetrical, but we know how to handle that. We simply name the two R groups. So 2-carbon chain is characterized by the term ethyl, whereas a 4-carbon chain is characterized by the term butyl. So it's simply an issue of placing these in alphabetical order as separate words in front of the word ether. So this would be butyl, ethyl, okay, ether, butyl ethyl ether. All right, butyl ethyl ether. So that's some simple nomenclature. Okay, it does get a little more complex. But before we go into slightly more complex ethers, let's practice drawing some structures from names. So I'm flipping over to page 102 of the lecture notes, whereby I've given you some systematic names. And here, we're going to draw the structures from those names. So sample problem 18.02 says provide structures for the following systematic ethers. Okay, let's take a look at that first one. The first one says isopropyl phenyl ether. So we know that we have an isopropyl group as well as a phenyl group attached to an oxygen. Now when you do this, you can draw these structures any way you deem appropriate. Okay? An isopropyl group, remember, is a 3-carbon chain whereby we bridge off the middle carbon. So I'm just going to draw this for convenience skeletally. So there's my 3-carbon chain. And I know it's isopropyl, so I'd best place an oxygen there. And what did we just learn? Yeah, a monosubstituted benzene ring is referred to collectively as a phenyl ring. Now, it's your option whether you want to draw alternating pi bonds inside or whether you want to draw the aromatic sextet of electrons. Either way is fine with me. So here's an illustration of isopropyl phenyl ether. Pretty straightforward. Let's look at the next example of cyclohexyl ethyl ether. Now, cyclohexyl means you have cyclohexane, but it means you've replaced one of the oxygens. I'm sorry, you replaced one of the hydrogens with an oxygen. So here I'm going to draw that oxygen at that spot, and now I'm going to attach an ethyl group. You could do this with a zigzag structure. You could write the letters ET, or you can do like I'm doing it, go ahead and draw it condensed, so long as what you're doing is legal. So this would be a cyclohexyl ethyl ether. Now let's move down to the sort of the middle of the page, and we're going to start looking at slightly more complex ethers. In other words, let me characterize that. It says other functional groups present. Okay, the ether component is called an alkoxy substituent. Okay, alkoxy substituent. Now let me explain what's meant by that. If you remember your R groups, things like methyl, ethyl, propyl, butyl, so on and so forth, that's all you need to know. Okay? But rather than writing methyl, you're going to write methoxy. Rather than writing ethyl, you're going to write ethoxy. So case in point, these are examples of alkoxy substituents. Notice we have a methyl group here, but we also have an oxygen. So this would be known as a methoxy group. So that would go in the name. Notice here we have an ethyl group bonded to an oxygen. So if you saw that, that's an ethoxy group. Similarly, a propyl group with an oxygen, that's a propoxy. What would be the next one? The next one would be butoxy, so on and so forth. So that's how we name those. Okay? So let's take a look at the two examples that I've provided for you, just so you can get a handle on how we're doing this. Recognize these groups. Okay? Okay, well, you know they're parts of ethers, and recognize that we have two of them. So collectively, that is known as what? That's known as a methoxy group. And we have two of them. That's known as a methoxy group. And you might notice, too, the way they're arranged in the aromatic ring for this disubstituted benzene is that they're in a para relationship. In other words, this could be position 1, that would make this position 4. So henceforth, the name of this compound is para, because there's two methoxy, dimethoxy benzene. So when you name it that way, you don't have a space between methoxy or benzene. It's all one big word. If you forget to do that, it's not a big deal. Okay? But that's how that would work. Let's look at the next example. The next example is a little bit more challenging than the ones that we had moments ago. What you need to do here, okay, is you have to recognize where the double bond begins. Now remember, you have to think back to alkene nomenclature, but in the name, okay, one of these carbons is carbon 1 and the other is carbon 2. So you have to take a path, okay, in this case clockwise, to get you to the first branching group. So that means this is going to be carbon 1, this is going to be carbon 2, and obviously that's going to be carbon 3. You wouldn't start numbering there because that would force you to go counterclockwise, and that would end up being carbon 5. You always move in the direction, so to speak, that gives you the lower number. Now, kind of like the previous example, okay, what do we have? We have a methoxy substituent. Okay, that's methoxy. So that's what we're going to call it. Now, where is the methoxy bonded in the ring? It's bonded to carbon 3. So this would be 3-methoxy, because that's where it's bonded. And because this is a cyclopentene derivative, 3-methoxy 1-cyclopentene. Now, in reality, folks, that 1 is redundant. So if I ask you to name some compounds, and you have the 1 in there, that's fine. But you certainly don't have to, because by default, that has to begin at carbon 1 anyway. So I'll leave it up to you whether you want to incorporate that 1 or not. Okay, so those are some examples. Now, let's use those as models to understand how to sketch some slightly more complex ethers. Okay? So look at sample problem 18.03. Notice here we have a disubstituted benzene ring, again. And we've seen these groups in the previous problems. Here again we have a methoxy group. Alright. And here we have a chloro group. So the rules haven't changed for how you name monosubstituted, disubstituted, polysubstituted benzenes. So in this case, you would simply go in alphabetical order. Alright? So if you're going in alphabetical order, that means that chloro would be first, followed by methoxy. And therefore that makes the chlorine position carbon 1, it makes this carbon 2. So you're going to have to include those numbers when you name the compound. So let's give that a try. The fact that you know that the chlorine is bonded to carbon 1 means that you can call this 1-chloro. Let me go ahead and write it down here. Dash 2-methoxy, okay, all one big word, benzene. Okay, 2-methoxybenzene. All right, here we go, benzene. So that'd be a systematic name for this compound. Now, a while ago I said that this, at least a fragment of this compound was called anisole, right? So if you wanted to call it an anisole derivative, right? In other words, remember what anisole was? Anisole is when you have a methoxy group bonded to an aromatic ring. You could call it orthochloro. We just put the O for ortho. Orthochloro anisole. So this is more systematic, and this is a more common name. Okay. Either way you choose is fine with me. Okay. Now, the last example I have here for sample problem 18.03, okay, we're going to have to follow what we've learned up there and the one just above it. So let's first recognize what this group here would be called. This is called an ethoxy group, right? In other words, that's an ethyl, but it has an oxygen, so hence it's ethoxy. And using the above example as a model, right, you'd have to start numbering such that you include both sp2 carbons, but you have to pass through it in such a way that you get to the oxygen here, the carbon bearing the oxygen, using the lowest sequence of numbers. So that means you'd have to start here. So that'd be 3, that'd be 4, 5, and 6 respectively. Now technically the only number that you need in the name here would be what? Would be the 4. Because it's telling you, the 4 is telling you where the ethoxy group is branched. Now, like I mentioned moments ago, if you want to include the 1, you can, but it's redundant. So let me just go ahead and write that down for you. So this would be 4-ethoxy. Okay. I wrote ethoxyl, but it's ethoxy. Take that out. 4-ethoxy dash 1 cyclo what? It's got a 6-membered ring. Cyclohexene, because it's an alkene. It's a cycloalkene. Right. So sorry about that. Right. Take that out. Right. Didn't mean to do that. So 4-ethoxy 1-cyclohexene. All right. Feel free to drop that 1 out as well because it's redundant. I'll leave that up to you. Doesn't hurt to have it. Doesn't make a big difference whether it's there or not. All right, let's move down the page. We're almost done with page 102. It says provide the structures, systematic names. I think most of you like drawing structures because you don't have to think about how to put the name together. You just look at the structure. Metabromo propoxy benzene. Okay. How would you start this? I think it's pretty obvious, so we're going to begin by drawing a benzene ring. Okay. If you want to draw the alternating pi bonds, or if you want to draw the aromatic sextet in the form of a circle, either way is fine, okay? So I've got the benzene component, and I need a meta relationship between what two groups? A bromo and a propoxy. So let me go ahead and sketch these in. So I'm going to put the bromine here, but I could have put it in any of the 6 possessions on there. But I need a meta relationship according to the name. So that could be here, or that could be there. Okay. So I'm going to choose here. So there's an O because I see the word oxy for oxygen. Propoxy means what? It means that we have a 3-carbon chain. And we just draw it all bunched up together like that. Okay? So that's an appropriate illustration for metabromopropoxybenzene. Okay? Let's do one more. Let's flip over to page 103 of your lecture notes. Now on page 103, I also have a nomenclature problem. So here we just have to look at the name very closely and identify the different components. We always start by looking at the parent name. So I see pentene here, but I see cycle in front of it. We're going to have a 5-membered ring. Okay, and it's got to have a double bond in it. So I'll leave that up to where you want to put it. Right, you can put it anywhere we want. So if I just choose to put it here, for example, right, that's my cyclopentene. But then it says 1-isopropoxy. So we have choices. We can put it there or there because remember, the double bond constitutes carbons 1 and 2 respectively. So if I put the propoxy group here, isopropoxy there, we're saying that's carbon 1. If I put it there, we're saying that's carbon 1 as well. So again, we need the oxygen, and I need isopropoxy, so I can sketch it that way. Okay? Now, similarly, if you want, you can draw these things condensed in a slightly different fashion. Let me just draw it one more time. If you prefer, you may remember that's a methine, and that methine has 2 methyl groups attached to it. So this would be okay as well. All right, you could just draw it next to it, put a bond there like that, however you want to do it. Either way that you're satisfied is perfectly okay with me. So that's the nomenclature for ethers. Anticipate 1 or 2 problems on your 3rd exam dealing with ethers. But what I'd like to do now is segue into preparing ethers. Now, interestingly, you've had this material before, back when we were discussing things like SN1, SN2, E1, and E2, back at the end of Organic 1. So you may have to go back and review that if you find this to be challenging. Otherwise, you can just follow along. So what I'm going to be talking about is how to prepare an ether. In other words, how do you make an ether? How do you actually make an ether? Well, there's more than one way to do it. But one of the most practical ways of making an ether is using something known as the Williamson ether synthesis. Okay? And the Williamson ether synthesis involves an SN2 reaction. Right? So the rules that you learn for SN2 are in place for the Williamson ether synthesis. So let me show you how that would work. To begin with, you need an alcohol. Okay, that's why I have an alcohol here on the left. And then what you would do, you would react that alcohol, preferably with something like sodium hydride. And sodium hydride is a really strong base, and it's especially suitable, okay, for this because the equilibrium lies entirely to the right by virtue of the fact that your byproduct is hydrogen. So hydrogen is a gas and it escapes. Therefore, the equilibrium is entirely to the right. So hydride acts as a Lewis base. Okay? It picks up that proton. And folks, alcohols have pKa's of like about 15 or so, give or take. So they're very weak acids. And what happens is that the bond would break here between the oxygen and the proton, leaving a pair of electrons behind. And so what you have is an alkoxide. You've heard me mention that word. Now sodium is just a spectator ion, okay? The sodium is just a spectator ion. So if I want to sketch it here, I can, but we need not worry about it, but it's there. Now, you don't isolate the alkoxide, all right? This is step one, but what you do, you introduce something with a good leaving group, right? For example, an alkyl halide. Now, you may remember that for leaving groups that are going to be attacked by a nucleophile, which the alkoxide is, this is now a nucleophile that you generated in situ. And this is the electrophile, which you added afterwards. Okay? In order for this to undergo an SN2 reaction, that alkoxide has to be able to get inside and literally attack that carbon from behind so that the leaving group can get displaced. Alright, so therein lies the SN2 reaction right there. This is SN2. And afterwards the leaving group will depart. Now remember, the leaving groups, the best ones are the conjugate bases of strong acids. So things like chloride break off really well, bromide, iodide, tosylate. But the rules are in place. This carbon needs to be sp3, which it is, but it cannot be hindered. So methyl would be the best, okay, and primary would follow. You can do this with secondaries to some extent, but methyls and primaries are the best. Tertiaries will not undergo SN2. As a reminder, the best leaving groups are chloride, bromide, iodide, and tosylate. Fluoride does not get displaced. So what happened? You made a covalent linkage between this oxygen and that carbon. Henceforth, you now have what? You have an ether. So this is called the Williamson ether synthesis. It's a two-step process whereby you convert an alcohol to an alkoxide, you introduce an electrophile, and then an SN2 reaction proceeds, and you end up with an ether product. Now what I have here in the middle of page 103 is an example of that. Okay, let's just take a look at how that would work. So what's going on here? In this case, we don't have an alcohol, but we have a species with an OH called a phenol. The phenols actually are very good because the protons are actually more acidic than our protons that you would have in an ordinary alcohol. So we're going to add sodium hydride, which you've come to know as a source of hydride, which is a really strong Lewis base. And what will the hydride do? It'll pick up this proton, okay? The lone pair stays behind, and then we get an intermediate called sodium phenoxide. This is the conjugate base of phenol. You don't isolate this, so let me go ahead and place it in square brackets just to remind ourselves that this is not something we're isolating, okay? We're generating it in situ. So overall, this is considered what? This is step one of the process. But where is step two? Step two is when you introduce your electrophile. Okay, in this case, what are you using? You're using a very active alkyl halide known as methyl bromide. So at this point, either of the three lone pairs on the phenoxide anion can act as a nucleophile towards the carbon bearing the leaving group. So let me just draw that arrow like that. Okay, and then we'll show the leaving group departing like that. And what have we made by virtue of this? We've made an ether. You may recognize it. We've seen it a couple of times already before. This is phenylmethyl ether, or the more common name is anisole. So your primary task, okay, would be to tell me what this product would be, okay? You don't have to be overly concerned about the byproducts over here, which are sodium bromide. Now, let's make sure we understand that. Let's move down the page to sample problem 18.05. Here, we've already generated some alkoxides, okay, from the corresponding alcohols, right? This is the tert butoxide anion. Okay, it comes from T-butyl alcohol. Let me write that in. This is called T, which stands for tert or tertiary. T-butyl, okay, alkoxide anion. Some people call it the T-butoxide anion, to be short. But I think you get the point. So what's it behaving as? Well, it's going to behave as a nucleophile. Why? Because it's the conjugate base of an alcohol. So this is nucleophile. There's our nucleophile. So you have that in a flask. And now what are you introducing? You're introducing the electrophile. In this case, we have an X and electrophile. So any of the three lone pairs, I'm just sketching one pair in, can now serve as what? A nucleophile towards the methyl group, and then iodide displaces. What goes in the box? Let's sketch it. You're going to have an ether inside the box. There's O. And what did you add to that O? You added a methyl component. Okay? So this is tert-butyl methyl ether. Okay, tert-butyl methyl ether. All right, let's go to the bottom. Now, I purposely set this up not to trick you, but just to remind you. What kind of reaction was this, going from here to here? What was it? It was an SN2 reaction. And why did that happen? Because this carbon, okay, is not hindered. But this carbon is hindered. So is this going to undergo an SN2 reaction? In other words, this is a tertiary alkyl halide, right? So therefore what? No SN2. Can't do an SN2, but you do get a reaction. Do y'all remember what was in competition with SN2 back in organic 1? You remember? Okay, what's in competition is E2. All right, E2. Now E2 means we have elimination bimolecular. So you might notice we have 9 equivalent protons from these 3 methyl groups. So let me explicitly show one of those protons, okay, and I'm going to convert that to a 2. I just chose one of those protons. Now this is a strong base, okay, this is sodium methoxide, which is the conjugate base of a weak acid known as methyl alcohol. And we have 3 lone pairs. I'm explicitly showing just one of those pairs. And can this get in there? Can this oxygen come in there and go like that? In other words, can it attack here? Can't. Why not? Because this is tertiary, it's too hindered. But what can happen? Folks, organic molecules are covered with hydrogen. So it's very easy for this to come along instead and remove that proton, any one of the 9 protons. And then that would be the first thing that happens. And the second thing that happens is we're going to have this pair of electrons collapse in between this, the alpha carbon, and that, the beta carbon. And then what happens next, the iodide will depart, taking its electrons with it. So this was the first thing that happened, 1. This was the second thing that happened, 2. And this is the third thing that happened. And what is this mechanism called? This is an E2 mechanism. It's in competition with SN2. And it happens with tertiaries on a regular basis. And so therefore we don't get an ether. What do we get? We get an alkene. So let me sketch the alkene. So 2 of the methyl groups that I've shown you remain intact. Okay, the ones attached to that alpha carbon. But the beta carbon is now part of what? Part of a double bond. So everything's accounted for. So in this case, you get something known as 1-methylpropene. I'm sorry, 2-methylpropene. Okay? All right. So that does it for that particular portion of the ether synthesis. Now let's try one on our own. Okay? Let's flip over to page 104. And I'm going to show you a couple more ways to make ethers. And then we'll take a break after that. So here you are, sample problem 18.06, and it's your responsibility to come up with a way to make this. Okay, and you notice that this ether is not symmetrical, right? On this side you have a T-butyl group, on that side you have an ethyl group. So this would be T-butyl ethyl ether. right? T-butyl ethyl ether. And in the directions, it asks you to tell me, okay, what alkoxide you would use and what alkyl halide you would use. Now there's a lot of clues there. Now an alkoxide means that you're going to choose some R group, okay, bonded to some O, negatively charged, and you can tell by the counter ion that we're using a sodium alkoxide, okay? An alkyl halide, in this case, would be a different R group bonded to some halogen. In this case, you can tell by the byproduct I'm pointing at over here on the right, it's going to end up being a Br. So the question is, where does the SN2 reaction take place? When this is an oxygen, does it attack that carbon and displace the leaving group? Or when this is an oxide, does it attack that carbon leaving group? It always attacks the least hindered side. So that's very critical in terms of figuring out where we're going to break this apart to figure out what compounds we need to begin with. So I'm going to provide a squiggly line right in between those, and that's going to allow me and you to separate that into two components. Squiggly line is right there. So the left-hand side is going to end up being, okay, our alkoxy substituent. So let me go ahead and sketch that with you. All I'm doing is I'm just writing down what I see on the right-hand side, but I'm going to add to it the features that are necessary to answer the question. So there's that part. And what does the other part look like? The other part's simply an ethyl group, right? So we've separated it into its component parts, but now we have to finish it. We have to provide, in some cases, a requisite atom and or groups or charges or what have you to make this proper. So I'm going to place my bromine here, okay, and then that's good because we have a primary bromide. And primary bromides, yeah, they're very reactive towards SN2. On this one, while it isn't essential to show the lone pairs, I'm going to show them anyway. Don't forget the negative charge, and I'm going to place sodium next to it as the counter ion, okay, and then just simply put a plus charge, plus sign, not a plus charge, in between these to indicate that we have two separate chemical entities. On this side we have a tert butoxide anion, and on this side we have a primary bromide. So what would happen is one of these lone pairs attack there, which it can freely do so. We get an elimination, we get a substitution, and that's how we come up with this ether. So I'm going to put the words S in letters, numbers there, SN2, to remind ourselves of that. So that's a simple way to make ethers using the Williamson ether synthesis approach. But there's another way to do this, and this goes back to Organic 1, particularly back to, I believe it was chapter 9, when y'all learned about oxymercuration, demercuration to make alcohols. Well, alcohols, as you recall, are very similar to ethers. They're kind of related. So we're going to use some of that chemistry that we learned back then to understand what's going to happen here. So here, let me just show you in a generic sense what's happening. Notice in the middle of the page we have this generic alkene, okay? And in step 1, we're adding a mercury 2 acetate and some alcohol. All right? Now, here's what you got to remember. This is the Markovnikov addition. So bear in mind that with Markovnikov, it's the more substituted carbon that will receive, in this case, a nucleophile, and then later the less substituted carbon will receive the hydride. Okay? So how does that work? It's a two-step process, and you can tell that by virtue of looking at these numbers in front of the chemical reagents. So here we have mercury 2 acetate. Okay, and folks, this is not catalytic; it's stoichiometric. Okay, if you're going to do this reaction in lab, you need however much of this you have mole-wise, you need the same number of moles of that, and the same holds for the alcohol. So everything here is stoichiometric. So step 1, what is step 1? Folks, in step 1, you're going to generate, okay, an intermediate, whereby the alcohol will go to where? Okay. The alcohol will go to the more substituted carbon. right? More substituted carbon. And that's Markovnikov competition. Okay? Alright, so let's just look at that one more time. The mercury component ends up going to the less substituted. Okay, so this is your intermediate after step 1. Notice that the RO portion, okay, ended up bonded directly to this carbon. So this carbon is now sp3, whereas it was formerly sp2. And the mercury component ends up on the less substituted carbon. Okay, so that would be this carbon here. Alright. And acetic acid is your byproduct. That came by the loss of one of the acetates and a proton that combined with it during the reaction. Alright, now you could isolate this intermediate if you wanted to, but we don't do that. It is covalent. But in step 2, what do? We add sodium borohydride. Right? So let me just put hydride here, okay? And I'll put some quotes on it because it's actually connected to a boron. And that hydride serves as a reducing agent, okay, by displacing the mercury component. And so in effect, you have Markovnikov addition. Let's go back to the original alkene. Here's our original alkene, right? And over here you have your ether. What have you added to it? You added the R group along with an oxygen and a hydrogen in the form of hydride to the double bond, but you did so in a selective fashion. So back in organic 1, all right, back in organic 1, you didn't have an alcohol here. You had what? You had water. Okay, so the chemistry is the same, and there you ended up with an alcohol. All right, so let's do some examples of that. Do like 3 examples, and then we're going to take a break. All right, look at sample problem 18.07. Folks, here we have styrene. Okay, styrene is vinyl benzene. And I'm looking at the reagents here, and I'm just being mindful of what's going to happen in an overall sense. This carbon here is the more substituted carbon. I'm going to write more substi, abbreviation. And this carbon here is the less substituted carbon. This is something you learned back in Organic 1. So we just have to give our final product. Now the final product is going to have select nuclei attached here, okay, and you identify that by taking a look at the alcohol that you're actually attaching. The less substituted carbon will always have one more hydrogen than we began with. Now bear in mind that we're only reacting with the vinyl component, not the aromatic ring. These pi bonds are stable. So let's go ahead and do this. Here's how I suggest you go about it. Go ahead and draw the skeleton you see there. Okay, just like you see it, but leave out the pi bond of the side chain. Leave it out. Okay, you can draw all the other atoms if you want to. Okay, so that's what I'm going to do. I'm going to draw every atom that I see there, but I'm purposely going to leave out the pi bond. And now all I have to do is go back in and look at these 2 carbons and make the distinction. Folks, look at the alcohol that you're adding. It's methanol. So that means you're going to add a methoxy substituent. Okay, so that's where that came from. And here, sodium borohydride means what? You added a hydride there. So you have it. It's that simple. It really is. Now, if you want to condense this down to a CH3, like that, okay, how are you going to draw it? That's be my guess. Now, let's do one more. And this one I'm going to kind of cut directly to the chase without drawing all the different things and identifying all this different stuff. What's your first step? The first step in all of these is simply to draw the compound that you see on the left-hand side of the page, but leave out for good measure that double bond. with a pi bond of a double bond, okay? Because you know you're going to add nuclei to those positions. Now here I wrote isopropyl alcohol. I need to spell that properly. Isopropyl, not isopropy alcohol. Isopropyl alcohol. Let's remind ourselves what that looks like. Isopropyl alcohol, we've had it before, is whereby you have a propyl group and an OH there, okay? So all of that minus that proton gets bonded to this carbon. Why that carbon? Because it's the most substituted. Okay? It's the most substituted. So here I can sketch that in. Probably should have left myself a little more space there. That's an isopropyl group, even though it isn't the world's most attractive isopropyl group. And of course I need one more hydrogen. Okay? So a little messy on my behalf, but I think how you can see how all this is coming together. All right, let's flip over to page 105, and we'll finish this up in just a matter of minutes. Now the other thing is, with how do you actually do this on your own? If you're in a lab and your job was to produce that ether, it's good to recognize that that's an ether. Okay? So we need an alkene, we know that. We have mercury 2 acetate, we have the reducing agent, we have to identify the alcohol. Now the alcohol component is easy to spot. Simply look for an alkoxy group. In this case we have ethoxy, right? So that means what? That means you need ethyl alcohol. So ethyl alcohol will provide an ethoxy group. Now you need a double bond, okay, and the best place to put the double bond would be here, okay, between this carbon and that carbon, not here and here. Okay, you need between here and here. If you have it the other spot, you're going to get a different regio isomer. Okay, so let me move over here and let's draw the cyclohexyl component of this. Okay, there's that carbon, right? Let me sketch it as a C. There's that methyl group. So we'll put in one hydrogen and change that back to a 2. Right? Okay, so this is vinyl cyclohexane. Alright, this is a good place to stop. We'll come back a little later and pick up the reactions that these undergo. Okay? Now don't forget, I have the all these notes posted from a previous semester in Canvas. So if you couldn't see exactly what I was writing there, you can download those and print them out to get a better idea. See you a little later.